Alright, this should be the last installment of this practice test video solutions. Start with number 23. Sphere starts from rest at the top of a ramp as shown above. It rolls without slipping down the ramp. Potential energy of the sphere Earth system is 0 at the bottom of the ramp. That's what we would have chosen anyway. Which of the following is true of the sphere when it reaches the bottom of the ramp? Its rotational kinetic energy equals the initial potential energy. That is not true because here we would have the gravitational potential, and then at the bottom it's rolling, so we have translational and rotational. So that rotational kinetic energy is not equal to that. The sum of these is equal to. Its translational kinetic energy equals the initial potential. No, that's not true either. Its translational kinetic energy and rotational kinetic energy are equal. For a sphere, that I think that this is true when you look at how it's split up between different objects with different rotational inertias. I think this is true for a hoop. I think when you have a hoop, it's a half-half split, and for everything else, it's not half-half split. So that's not true. The sum of its translational kinetic energy and rotational kinetic energy equals the initial. Yes, that's true. Sum of its initial equals the energy loss because of friction. No. All right, so there we go. That's a D. Now, if you're wondering, if you're thinking to yourself, like, how could I possibly do these 35 questions in 45 minutes, Mr. McGrath? You can't even do them in that amount of time. I'm taking more time to talk through these things than it would ideally take you to do them. So please keep that in mind as you go through. Anyway, number 24. Two horizontal disks of mass m have the radii shown above, r and 2r. Disk A is attached to the axle, spinning freely. Disk B is not attached to the axle until it rests. Drops down. When both disks spin together without slipping, the initial angular velocity of the disks is... Okay, so this is a conservation of angular momentum. It's like a collision, right? This is going to drop onto that, and they're basically going to stick together and become like one rotating disk. So the initial angular momentum is equal to the final angular momentum. Initially, it's just this one that's rotating, so its angular momentum is I omega. It's a disk, so that's 1/2 m r squared times omega initial is equal to, and then afterwards the two disks stick together and we add rotational inertias just like we add mass. So that's 1/2 m is 2r squared. That's the rotational inertia of this, plus this one on top, 1/2 m r squared times omega final. And then we just got to clean that up, right? Omega final equals. So what do we have here? We have 2 squared times 1/2, so I got 4 mr squareds. And then here I've got 4 mr squareds plus 1/2 an mr squared. Right? I'm pausing here because I don't think... Oh, this is 2. Sorry, that's 2 there. I'm not seeing the answer that I want there. Let's see. I think I've got everything here. Let's just run through the numbers again. So 1/2, 2 squared, that's 4. 1/2 of that is 2. And then I've got, oh, that's because that's 2. I'm sorry, I didn't fix that. That's why. Dummy. So if I double both of those, that's 4/5. Omega 0. There we go. Sorry about that. Okay. Satellite is in circular orbit such that it stays directly over the same point on Earth's equator. That is called geosynchronous orbit. Which of the following must be true for the satellite? It must have a specific mass. So what we want here is it has to have a particular period. So what does that period depend on? Period is equal to, if you remember Kepler, period squared is equal to 4 pi squared g. You need to be able to derive this as r cubed. So period depends on radius. And this mass here, this is the mass of the thing in the center, not the mass of the satellite. So does the satellite have to have a specific mass? No. Does it have to have a specific altitude? Yes. It has to be at a certain distance. Does it have to have a specific angular velocity? No. The angular velocity, if it has to be at that radius, that's going to determine the velocity in circular orbit is gm over r, the square root of that, right? So it is, if this is some particular thing, then so is this. So those are both true. 2 and 3. All right. Spheres X, Y, and Z have masses and locations indicated. What is the magnitude of the net gravitational force on sphere X due to the other two spheres? Okay, so net gravitational force is g m over r squared. That's the gravitational force from this one on sphere X, plus g m over r squared. All right, so I just got to clean that up. So that's a gmm over r squared plus, this is a half of a gmm over r squared, right? Because there's a 2 there, and one of the 2's will cancel. So gmm over 2r squared. And then I could do that to get a common denominator, so it looks like 3 halves. Oh, dang it, that's not there. Keep messing the easy math up. What did I do this time? 2 r squared. Arg. Oh, sorry. This distance is 3r, not 2r. Dummy. Gosh, dang it. Okay, so that's not going to cancel then, so let's not do that. So this is 2 over 9, and then that would be 9 over 9. So it's 11 ninths. Sorry about that. Gosh, math. All right, so 26 is C. Oh, and there's more problems on this page. 2 identical satellites of radius orbit a planet of radius r. Sorry, planets radius r in circular orbits A and C of radii 3r and 12r respectively. Okay, how does the magnitude of the gravitational force between the planet and satellite in orbit A compared to the magnitude of the gravitational force? So this, I'm just going to do this with proportional reasoning. Gravitational force is directly proportional to gmm over r squared to r squared, right? So going from here to here, you're quadrupling this, which means it's going to change by a factor of 16 because the r gets squared. So the force on A is 16 times stronger than the force on C. This is correct because of the r squared. We're going from 3 to 12, that's quadrupling, and that quadrupling is getting squared right there. Okay, speed of the satellite, the ratio. Okay, so in orbit A, I know that in circular orbit, you need to be able to derive this, but you should know that that's gm over r, right? So this one would be 3r, and then this c would be gm over 12r. And they want to do the ratio here, so I'm just going to be careful to make sure that I get it the right way around, because it looks like they have like the upside down versions of some of them set up there to mess with me. So if I want this one over this one, that's the same as this times the reciprocal of that. So VA over VC is equal to VA, and I can put these all under one big square root sign because you can do that with square roots. Reciprocal of that, GM 12R. So everything cancels. 12 over 3 is 4. Well, that's 2. 2 over 1. That's number 28. At the surface of the Earth, an object is suspended. That's funny. After these gravitation problems, they're just reminding us here that we're back on Earth. At the surface of Earth, an object is suspended by 2 cords, this one and this one. One cord is horizontal and one is at an angle to the horizontal, as shown in the figure above. Tension in the horizontal cord is TH. If the assembly is moved to the surface of a we are going to a different planet. Planet with the same average density and twice the radius of the Earth, the new tension in the horizontal cord. Okay, so the first thing we have to realize is whatever happens if like we have twice as much gravity or whatever, that's going to affect the tensions in these in a linear, like it'll be directly proportional to. So whatever the change in gravitational force is, then we're going to get the same thing. Now the mass of this little thing is going to stay the same, right? The same assembly. So it's going to depend on these things. So the same average density and twice the radius of Earth. Okay, so we got to think about that. The density is the same, but the radius is twice as big. So we talked about this when we talked about the like gravitation inside of a sphere. If you double the radius of this thing, but it's got the same density, doubling the a linear dimension is going to increase the volume by a factor of 8, right? So the mass of this new planet is 8m, and the radius of it is 2r. Right, we have to recognize that it's got the same density. That means doubling the radius is going to increase the mass by 8, right? Because radius or the volume is 3-dimensional. So that means that if I put an 8m here and a 2r here, the 8 doesn't get raised to any power, but the 2r on the bottom, that gets squared. So I have 8 over 4. The gravitational force is going to be twice as much. So that means that all of the tensions here will double. More proportional reasoning, they love it. We love it too because, I don't know, it's not that hard, right? A space shuttle has a mass of it has some math, and it also has a mass of 90,000 kilograms. In order to stay in circular orbit, it must have a velocity of this. The pilot discovers that the shuttle has slowed down to this, and the shuttle's speed needs to increase. If the thrusters exert a constant force of this, how long do the thrusters have to exert this force in order to return the shuttle to orbital velocity? Okay, so this sounds like we have a mass. There's a mass, and we have this force, and we want to know how long. So force times time is equal to what? If we have a constant or average force times time, that is equal to mass times change in velocity, right? Impulse is equal to change in momentum, right? What should tip you off that it's this? We have a force acting over a period of time, so that should point you in the direction of impulse momentum. That force is 50,000 newtons. The time is what we're looking for. The mass of the shuttle is 90,000, and we need to change the velocity from we need to get back to a final velocity of 8,000 from a velocity of 7,900. So 90,000 times 100 divided by 50,000. Probably doable without a calculator. There's 4 zeros to go away, so 100 divided by 5 is 20 times 9 is 180, so 3 minutes. You can use your calculator, of course. So 30 is D. A pendulum and a spring both have a 1 kilogram sphere attached to their ends and have the same length when in equilibrium, as shown. They both oscillate with the same period. If the 1 kilogram spheres are replaced with 2 kilogram spheres, and the amplitudes of oscillation are unchanged, which of the following is true about the resultant period of oscillation for each? Well, the period of a pendulum is equal to 2 pi times the square root of L over G. And notice here that the mass does not make any difference here, right? So this is going to be, you double the mass, that's going to stay the same. And period of a mass on a spring is equal to 2 pi times the square root of m over k, right? Those are both right there on your equation sheet, aren't they? So if you double the mass here, that is going to increase the period by the factor of the square root of 2. So for the pendulum, we remain the same, and the period of the mass on the spring is going to increase. That 31 is B. All right, systems A and B contain identical ideal springs. Ideal spring just means that force is equal to kx, Hooke's law, that can slide along a surface of negligible friction. In system A, the surface is horizontal, and then this one we got it at an angle. Initially, both blocks are at rest and in equilibrium. Each block is then pulled the same distance d in the direction shown, and then released. And we got all these questions are about these. After the block in system A is released from rest, the time for the block to first reach a maximum speed is delta t. So that is, maximum speed happens at equilibrium. That's where all of the energy is kinetic energy. So that time is going to be different things we could say about that. The time that it takes to get from here to here, that's 1/4 of a period. After the block is released from rest, the time for it to reach a maximum speed from here to here is delta TA. After the block in system B is released, the time for the block to first reach a maximum speed is, okay, so what's the difference between these two? Well, the period of mass on spring is equal to 2 pi times the square root of m over k. So what have we changed when we make this at an angle? Have we changed the mass of the thing, the identical blocks? No, and it's the same spring. So the period is going to be the same because it does not depend on what's going to happen here is because this is tilted a little bit, we are going to have the equilibrium position is going to be a little bit different because there's a little bit of gravitational force, the sine component of gravity. But it doesn't matter. The amplitude, how far you stretch that, doesn't matter. Look at what this depends on. Period of mass on spring, it depends on the mass of the object and the spring constant, not the other things. So 32 is just A. It's the same. For 33, for system A, when the block is halfway between its release position and it's like the amplitude there, and its equilibrium position, the block's kinetic energy K and the elastic potential energy of the spring block system is U. The ratio, so we did this was a homework problem, we did this exact problem. So what is the split here? Well, when it's here, when all of the energy is in the spring, we could say that the total energy is 1/2 Ka squared, right? And here we have the potential energy would be equal to 1/2 K times half of the amplitude squared. So if we simplify that, that's 1/8 Ka squared. So what does that mean? It means that when we're at this halfway position, because the amount of energy stored in the spring, the potential energy depends on the square of position, then here, when you cut that in half, it's actually a quarter here of what it is here. So if we were going to make like a little pie chart, when we are here, we have all potential energy. When we are here, we have a quarter as much, so that would be a quarter, and then the rest of it must be kinetic energy. So what's the ratio K to U? It would be 3/4 to 1/4, or 3 to 1. I think there's different ways you could get at that, like other maybe mathier ways of doing it. I don't know. But that's what we need to realize, that it's a quarter of what it was there, so the other 3/4 is kinetic energy. A student wants to use an apparatus similar to System B to measure the acceleration due to gravity G. If the mass of the block, the force constant of the spring, and the angle of the incline are known, what additional data must be measured to determine an experimental value for G? So let's see. We need to So let's make a force diagram for this thing. So what they would need to do, they would need to come up with some kind of equation that has G in it, and then know everything else. So this would be like mg sine theta here. That's got a G in it. And if we could measure, if they could just measure what this here, if they knew how much it was stretched here, if it was just at rest right here, and they knew what this, how much it was stretched from its equilibrium position, because if you tilt it, right, the that spring force would have to be equal to this. So Kx would be equal to this. And what do we, students want us to know? We already know the K. We know the angle. What additional data must be measured? The stretch of the spring at the equilibrium position. We would need to know that, right? So we could know how much more it is stretched here. I'm sorry, that's just to know, yeah, to know this. So we could calculate this Kx. I guess I would word this, I'm pausing here because I guess I would have said the stretch of the spring, like, I guess you could say like from the equilibrium position that it would be at in System A. So either way, what we're talking about, what they're saying here, is like how much it's stretched from like where it would be relaxed without this thing on the downward slope of that ramp. For 2, the speed of the block as it passes. We don't actually need to put it in oscillation at all. We just need to do this equilibrium thing. The time, and so we don't need to do that. All we need to do is just know how much more it's getting stretched there, and then set this equal to that. set this equal to that. That's what they would have to do. So just number 1 is all we would need. Last problem. Another spring. My goodness. A 2 kilogram block is attached to a string that passes over a pulley. It's attached to an ideal spring. Pulley and the string have negligible mass, negligible friction in the pulley. So just talking about forces here. Block is held in place, the spring at its original unstretched length, and then released from rest. The amplitude of the resulting oscillation is most nearly... Okay, so what are we doing? Pulley, where the block is held in place with the spring at its original unstretched position, and then we're going to release it. And we want to know what is the original unstretched length. And okay, so let's see if we can figure that out. We want to know the amplitude of this. When we release this, this is at x equals 0. Okay, and this just goes over this pulley one time, so however much this changes, that is also the amount of stretch in the spring. Okay, so I think we can do that. Can I convince you that the amplitude of oscillation is going to be, or that this thing is going to bob up and down over the position where the forces are balanced? So that means that the amount of stretch here, from like right now, this is not pulling on the spring at all. This is when the spring is just relaxed, and then I'm going to release this. So now, if I did that very, very gently, then how far would we go down to the equilibrium position? Well, we have force of spring would be equal to the gravitational force pulling down on this. That would give me a kx on this side is mg. I'm just going to use 10 like they suggest because that makes it easy. So x is going to be equal to 20 divided by 100, or 0.2. So that is the distance from here down to this equilibrium position. And then that's the equilibrium position. It's going to go past that and then oscillate back and forth from the equilibrium position where it would be if we gently brought it to rest. So that's going to be 0.2 meters or 20 centimeters. All right, there you go.